Hi class, we are working on work, power, and efficiency today. We're reviewing quite a lot, going over two objectives, Objective 3 and Objective 5 of the Unit 1B overview. Um, they state that we can identify the various types of energy and work in a system, can identify and calculate a change of energy or work. And if we focus on Objective 3, I know we are going to identify the types of mechanical energy that exist. We're going to use evidence to describe and calculate all types of energy present with a focus on just describing. So I'll kind of highlight that for next time. We're going to define and calculate work done as the product of the component of force parallel to the displacement. That's what we're going to do today. We're going to calculate work from a force displacement graph. And we're going to derive a joule from the fundamental units, kilogram, meters, and seconds. So we're doing a lot there. As we move forward to Objective 5, we're also going to apply the concepts of power and efficiency, is specifically defining and calculate power as the rate of change in energy or the rate of change of work done. And then we're going to relate power to the force and velocity. And we're going to calculate efficiency by identifying lost or wasted energy. Now, one thing to note is these concepts, even though it seems like we're going through a lot, we're going to be continuing to work through each portion of this pretty much our whole time in physics, because energy, power, efficiency is embedded in like the soul, the heart of physics. So first, similar to last year, I believe we've seen this infographic, which we talk about the different types of energy, mechanical, which may consist of kinetic and potential, gravitational potential energies. And we talk about sound, chemical, electrical, light, heat, nuclear. But really today we are focusing on mechanical. It's not until later that we might focus on the other ones. So this is the major one we're focusing on today. There it is, mechanical energy. This mechanical energy is a sum of an object's kinetic and potential energies, measured in joules. So first, before we get to this concept of joules and the concept of energy, we need to talk about how this energy, where it really comes from, how can we identify it, and that goes with the statement of work, the concept of work. It's a transfer of energy. Work done is the amount of energy used or transferred to make something happen. And usually that transfers just between different types of energy. So whether it's gravitational potential to kinetic, whether it's kinetic to thermal, the work done is going to be the same equation every single time, the same idea. So in this picture, we have a person dragging a box on the floor. They travel some distance d, and they apply some force F at some angle theta. You might see that there's kind of this dotted line right here. That's the horizontal vector of this force. And there's also this vertical vector of this force. So if we were to draw a free body diagram, one, it would of course have the force that she's pulling on. And then we'd have a gravitational force downward. And then we'd have a smaller normal force because some of the normal force would be taken from her pull upward. So that would come from this little section right there. But that's just, side note. But most importantly is, what about the other force? What about the horizontal force? So let's give this a name. It's in red, so let's do it F kind of X, right? Because it's the horizontal force. Now that's the force that she is pulling across some distance d. One thing we might want to say is there friction? And whether there is or not doesn't mean she's not doing work. It just means where is the energy going into. If there is friction, then she's pulling against friction, and the cart is probably not accelerating because she's pulling at a constant velocity, and that work that she's doing is being transferred into some sort of thermal energy in the friction. If there is no friction, well, then the object is definitely accelerating and increasing some velocity. So let's look at where this what equations we can use with this. So first, work is a change of energy. So the most basic statement I like is just work is equal to some change in energy. Now, it's not so much usually that the change in energy is the work, is that work has to be done to transfer that energy. I like to see work as kind of the currency, like energy currency, where you may have a bank account with a bunch of different, accounts in there, savings, checkings, and so forth. And I like to identify those accounts as actually energy accounts. So, like, we have a kinetic energy account, we have a gravitational potential energy account, we have a thermal energy account. We have all these accounts, and work is the transfer between these accounts. So, if you ever make a bank transfer from one of your accounts to another, say you have a lot of money in your checking and you want to put in your savings, work is the transfer of that amount. In order to actually get a calculation for it, it's given by work is equal to force times displacement times cosine of theta. And so in this case, this is really actually force times cosine of theta times d, which is the same equation, but I put F cosine theta because F cosine theta is this force of x, right? That's your F cosine theta. So what we're doing by including the cosine theta in this F and d is we're trying to find the parallel components for force and the displacement traveled. So once I did F cosine theta, then I found this horizontal component, and it's parallel to D, where theta is the angle between F force and D distance traveled. This is your work done. And the units for work, well, it's a transfer of energy, so really the units are still joules. And you can see that these units are force times distance, so this comes from Newton times meters, which, if we were to break it up further, just so we have some identification of these variables, Newton's is, right, mass times acceleration, so kilogram times meters per second squared. So we have kilograms times meters per second squared times meters. And that gives you kilogram meters squared per second squared. And these are the SI units for joules. Kilogram meters squared, let's make sure that M is clearer, meters squared per second squared. Now, that doesn't really mean a lot. It just helps us if we ever want to try to process another situation and we end up with kilogram meters squared per second squared. We might think, hey, that might be energy, and we can pursue that. So when work is done, then we're applying a force over a given displacement. And depending on how fast that happens, that's going to tell us how powerful something is. So this may be a motor that's lifting up an object, lifting up a car. This may be a car pushing the engine pushing the car forward. Whatever we want to say, this is power, and we call the units for power, we use watts, which is our watts. So it's measured in watts. And power is the rate of change that work is done. So power is equal to work divided by time. So P is equal to W over T. And that's a rate of change of work that's done. And we need to identify efficiency if we're dealing with power, because when we're dealing with power, we're generally dealing with engines, with motors, with something where we have some input power and we have an output power. So efficiency is just pretty much the definition of efficiency, right? How efficient is something? How good is it at doing what it's supposed to do? So this efficiency, which we say E, and it's unitless, by the way, is equal to the power out, or energy out, over energy in, or power out over power in. And E is always going to be always less than 1, but of course greater than 0. All right. So now we're going to look at how this work transfers energy. What energy does it transfer into? But first, let's talk about what positive or negative work is. So positive work is when energy is given to the system or object, and negative work is when energy is removed from the system or object. The positive or negative usually comes from the angle between the force and the displacement. So when cosine of 0, for example, that means that force and displacement are in the same direction, then we have positive work. If force is acting against us when we travel that displacement, we're going to get negative work. But we'll have a lot of experience with this as we practice. So where does that positive and negative really mean? Like how is it removed or how is it added to the system? Well, we come up with the work energy theorem, which is our like overall main key point for this work energy relationship. And although I've said that work is equal to the change in energy, it's more common that you'll see work is equal to the change in kinetic energy. So EK, so that's the change in kinetic energy. And we're going to talk about that more. We've learned kinetic energy in the past. I think we already have the equations for it. We're going to explore that more in a little bit. But first, let's actually look at other forms of that work can be done. So gravity can actually do work on an object. And we call that ability to do work by due to gravity, gravitational potential energy. So it's energy stored in an object due to its position in a gravitational field. But really all that means is it has the ability, right? It has a force of gravity acting downward, and it may travel downward some distance, in which we use h, we don't use d in this case. Well, if it does travel that distance, well then we have the work due to gravity as the force of gravity times this distance, or h. And when we do this, we end up with mgh, and this is our potential energy. Now, we've seen this before, but really this is just our work due to gravity as seen as a gravitational potential. But if the work hasn't been done yet, it hasn't traveled that distance h, then it's potential. So it's the ability to store that gravitational potential energy. More often though, we'll see this as change in EP, because we don't like setting a height to be 0 unless we have to, unless it's a situation. So we like to see this as mg delta h. That's the change in gravitational potential energy. You might also see it as like EGP if we want to be explicit, because there are other forms of potential energies. Like, I think we go into this one, yeah. So we have elastic potential energy, which is the energy of an object by compressing or stretching a spring-like system. I give an example because this equation, this relationship is really F is equal to K delta X. And there's a negative in there, but they kind of disregard the negative in this case. But we don't need to worry about that. We just need to worry about how can I solve for an energy if a spring is compressing or stretching between, we're going to say 7 meters somehow. Well, there's a force in the y-axis and a displacement in the x-axis, and I know that work is equal to force times displacement. And previously we've said when there is a graph that has a changing value, such as force, and we need to find the product of force and displacement, but if force is changing, then we can find the area under this curve. So we end up with another situation where we have to look at the area under a curve to calculate some value. And if we do that, I end up with, right, this is my work done due to like a spring, let's say, so maybe I'll call this like work due to a spring is equal to 1/2 times the base times the height. Well, that's 1/2. The base is the change in x, which we use, right, we see in this equation right here. And the height is the force due to this spring, right? But I can plug in that force due to my spring, which is kx, and I get 1/2 delta x times, and let's get rid of that negative just because this graph doesn't show a negative. If it did show a negative, we'd have to include it, but it doesn't. So 1/2 delta x times, and then k delta x. And look at this, I get 1/2 k delta x squared. And this is my energy, my potential energy, and we call it like P as well, but this in this case is like more so your elastic potential energy. So that's the way that we also like to say it. In your data booklet, this equation is in your data booklet. This equation is also in your data booklet. And like I said, they don't differentiate the EP. So you just have to know when it's mgh, it's gravitational. When it's 1/2 kx squared, then it's elastic potential. So these are both potentials that have the ability to do work, right? If they fell or if they were released from the spring. Well, where does that work go? Well, like we said, it goes into kinetic energy. So let's actually identify kinetic energy. This is just the energy of an object due to its motion. This is 1/2 mv squared. Ek is equal to 1/2 mv squared. And this is the object's energy due to its motion and mass. One thing to recognize, if there is a change in Ek, then we cannot do 1/2 m and then v minus u squared. This is bad. You cannot do that because if we were to look at an initial kinetic energy and a final kinetic energy, I would have to separate those equations. So I have 1/2 mv squared minus 1/2 mu squared. That's my change in kinetic energy. So just to be clear, you cannot just subtract the v and the u and then square that. That's just mathematically incorrect, and it's a mistake that does happen. But all right, so we have the forms of energy of gravitational potential, elastic potential, and those have the ability to do work on an object to give it kinetic energy. There are other types of energy, such as thermal energy, that we can only calculate by first finding the initial total energy, the final total energy, and determining if energy was lost due to thermal energy somewhere. All right, I have a sample problem that we've seen already. We've seen this in the previous one of the previous practices, in which a car's mass is 8,500 kilograms and is driving up a road at a constant speed of 6.2 meters per second. The car's motor is creating a force of 21,000 kilonewtons. So I know there's a force forward that's 21,000 newtons. In this practice problem before, we calculated the parallel and perpendicular components of the force due to gravity, and with that calculated the frictional force that acted opposing the motion. So I would like to include those on this diagram so I can put a force of friction, which is 12,300 newtons, and a gravitational force, which is 8,300. Yeah, it's 8,700 newtons. So it's 8,700 newtons. And that's due to the force of gravity, parallel, and this is the force of friction. So force of gravity, parallel. I'm not going to include the downward gravitational force or the normal force acting perpendicular to the surface because they're not useful for me. If I were doing a free body diagram, I would. And then I'm going to calculate these 6 things. So we have 1, the displacement traveled, 2, the change in kinetic energy, 3, the work done by gravity or the gravitational potential energy difference, and the work done due to friction, and the total work done by the car, and finally the power during the 5 seconds it traveled. So it drove for 5 seconds. So let's just knock these out kind of one by one. So I know the displacement traveled, well, it travels for 5 seconds. So I can take its velocity, 6.2 meters per second, and multiply it by the time because there's no acceleration. So 6.2 times 5 ends up being 31 meters. Let's find its change in kinetic energy. Well, it's traveling at a constant speed, so there's no energy, right? Change in Ek is equal to 0 joules because there's no change in velocity. So that being said, it's like, oh, then there's no work done, or no work done is transferring to kinetic energy. That means there must be work lost somewhere. There must be thermal energy transfer because energy can't just disappear. It has to transfer to something. So let's find the work done due to gravity. And we're going to find this a few different ways. We know that we can see the work due to gravity as finding the gravitational force times the height times the cosine between And there's a lot of different ways to solve for this. Let's just start with our work done equation. Work due to gravity is equal to the force of gravity times displacement times cosine of theta. Now in the end, this should be equal to just force of gravity times height, because force of gravity and height are both in the vertical direction, and so that should be fine. So let's see if we can get there. Let's redraw our image of the car. Here's 6 degrees, and there's a force of gravity acting downward. Let's zoom in. And we know the car is moving upward in this direction, so let me draw a vector in this direction, and we just need to find this angle right here. Now you might look at this and see something familiar, and we've drawn this before. We've drawn this when we draw our components, our perpendicular components and our parallel components, and we've done this by saying, okay, we can identify this angle. That angle is the same as the angle 6 degrees. And so that's how we're able to find this component, this parallel component. So we could just use that if we wanted to. So one step we could say, well, why don't we just find force of gravity parallel and then multiply that by the displacement. That is the same as force of gravity times s times cosine of theta. We could do that, or we can find our force of gravity and just multiply it by our height, because we are finding the parallel component of our displacement, so our vertical component of our displacement. Both of these work, but we end up with the same equation. So when we found our force of gravity parallel, though, we used sine of 6 degrees. So why do we use sine if we want to, we look at the equation and see cosine? And that's because we use the sine of 6 degrees at this angle right here. And we really want to use cosine of this angle. So we can see that, well, we know the orange angle, right? That one is 90 minus 6 degrees, so that's 84 degrees. That's this right here. And so one thing to remember, if you remember trig, the sine of 6 is equal to the cosine of 90 minus 6. So that's equal to cosine of 84. So whether you start with force of gravity parallel and multiply it by the displacement, that's going to get you the same work, because this is parallel to the plane. So what you've done is actually you found the parallel component of the gravitational force, which is parallel to the displacement, or you find the vertical component of the displacement, and so then both force of gravity and height are both vertical. So as long as they are parallel with each other, then you can use this equation. So we end up with force of gravity times displacement times cosine of 84, which is the same thing as force of gravity. I'm going to move s to the outside, because force of gravity times sine of 6 times displacement. And we already solved for force of gravity times sine of 6. That's just the parallel component of the gravitational force, so that's 8,700 newtons. So 8,700 newtons times the displacement traveled against that force, and that gets us to a big number. That gets us to 2.69. Ooh, that's, how should I write this? Let's just do it all. I'll just write it all. 269,700. So that's 269,700 joules. Now, one thing to recognize, though, and it's kind of hard when you have these like weird angle situations, is that the direction of displacement is opposing the direction of the gravitational component. And so that means that the gravitational component must be trying to take work from this system, right? It's not supporting the forward motion of the car. So this should be negative, and you just have to kind of think about that when doing problems. Sometimes it's easy and you can actually use the angle and it works out. Most of the time you have to think, is it working to push the object forward or to pull the object backwards? And that's how you say energy is going into the system or object, or out of the system or object. All right, so we have our work due to gravity. Let's find our work due to friction. This one should be a little easier, as the work due to friction is equal just to our force of friction times our displacement times cosine of theta. And this is where I say it's going to be easier to see the negative, because we know the force due to friction is opposing the forward motion of the car, so we know it's going to be negative. So what's our angle between our force due to friction and our displacement? Well, our force due to friction is acting against our motion, which is happening forward, so the angle is going to be 180 degrees. And what's cosine of 180? Well, that should be -1. So force due to friction, we said we calculated it, 12,300 times 31 times cosine of 180. And this gives us negative 12,300 times 31, 381,300. So negative 381,300 joules. All right, we're not done yet. I know this is a long problem, but trust me, there's a purpose to this, so stay with me. Number 5 is total work done by the car. So if we want the work done, kind of like the applied force, the engine's work done, we need the total forward force, the engine's force, which is 21,000 newtons, times 31 times cosine of theta. Now, in this case, we see that our theta is 0 because the direction of the force is parallel and towards the direction of the motion of the car. So this theta would be 0. So we have 21,000, 21,000 times 31 times cosine of 0. Cosine of 0 is just 1, so we don't have to worry about that. So 21,000 times 31 is 651,000. So when we say how much work was done by the car, then we have to start thinking about, well, what's happening to the kinetic energy? Because we said that the work, and really it's the total work, is equal to the change in kinetic energy. Well, we already spotted this and said this should be 0. So let's add these up. We have 651,000 plus negative, so just minus 381,300 minus 269,700. You might see this. When you add these up, well, this ends up being 0. This checks out. So all of the energy was transferred somewhere. It was either transferred to like the gravitational potential energy as it went up the hill, or it was transferred to thermal energy due to friction, due to the force of friction times displacement. That all came from the applied force of the car. And if we were to look at 6, the total work, the power during the 5 seconds, well, this is specifically the power of like the applied force from the car. So this is 651,000 per 5 seconds. 651,000 joules by 5 seconds. And so this just gives you about 130 kilowatts, or 130,000 watts. Now, one thing to recognize, power during the car, or power during the 5 seconds of the car, it should say of the car, or else you might think it should just be 0, but that's actually asking it from the car. Now, real quick, we're done for the most part. We just need to recognize that when we have a force displacement graph, similar to all the other situations, when we look at the units and say, hey, look, my area under the curve is force times displacement. Hey, I know what that is. That's going to be equal to my work done. So the work done on a force displacement graph is just the area under the curve. All right. I hope this was helpful. I'll see you in class.